Hello, everybody. Welcome back. Today we're going to be looking at Unit 8.3, which is all about weak acid and base equilibria. The last unit, or the last subunit, we looked at strong acids and bases. Today we're going to be looking at weak acids and bases. So let's get started. All right, so we're going to be addressing acids and bases separately, and we're going to start off with acids. And let's just look at a general reaction for the dissociation of any acid in an aqueous environment. And what I'm using as any acid is the formula HA. Of course, there is no element A. Okay, so this could represent any acid. And let's review a little bit of vocabulary here. Remember, guys, that a Bronsted-Lowry acid is a substance that donates a hydrogen ion. So sometimes it's called a proton donor. And a base is something that accepts that proton or that hydrogen ion. So in this circumstance, this is my acid. Water is acting as the base. And if you will look, what HA becomes after it donates that hydrogen is A minus. Remember, that is referred to as the conjugate base. And what the base becomes after it accepts that hydrogen ion is called the conjugate acid. So I just wanted to review those vocabulary terms with you. And this reaction is what occurs whether an acid is strong or weak. Okay, it doesn't matter. Now, remember, guys, that a strong acid means this reaction proceeds 100% or nearly 100% in the forward direction. Weak acids, on the other hand, proceed in the forward direction only a little bit, okay, to a limited extent. And so we have to talk about equilibrium for weak acids and bases. And for weak acids, we will very often write equilibrium expressions, just like this, okay? Weak acids have what we call Ka values. That's an equilibrium constant. That little a just stands for acid, okay? And all this expression, you know, the place where that's coming from is this reaction. Why is water not included in that expression? Of course, because it is a liquid. Liquids are excluded. Okay, remember, guys, that H plus and H3O plus represent the same thing. So you can write an acid's dissociation, its equilibrium expression. Either way, they mean the same thing. Okay. And as I said, we deal with equilibrium for weak acids. Strong acids do not have Ka values. Their Ka values would essentially be infinity, okay, because the reactions go essentially 100% in the forward direction. So we will only ever see Ka values given for weak acids. So as I said, weak acids do not dissociate completely. The equilibrium does not go very far to the direction in the forward direction. It goes mostly in the reverse direction or towards the left. We will be given Ka values anytime you're dealing with a weak acid, and they are typically very small numbers because that equation we saw on the previous slide proceeds very little in the forward direction, very little product. And leading into that, if there's very little product, H plus was one of the products. There will be very little H plus. Most of the acid, guys, is going to stay in the HA form. Very little of it is going to break off. Okay, some, but not much. Okay, and we'll talk about that statement a little bit later. Now, if you'll remember from the previous lesson, there were 6 strong acids that I said you should commit to memory. Any acid that is not one of those 6 is a weak acid. And guys, there's nothing to memorize. You don't need to memorize your weak acids. It's just If that acid is not one of the 6, then it must be weak. I've just given you some examples here of weak acids, but nothing to memorize. Okay, again, you know, if you focus on the graphic on the left-hand side, okay, what's being represented at the top is a strong acid. Please notice that after dissociation, most of this acid has been ionized, dissociated into H plus and A minus. So what's represented up here, that's showing a strong acid, whereas down here is a weak acid. And if you'll notice, after dissociation, does the acid dissociate some? Yes, but not very much. Very, very little. Most of a weak acid remains in its intact form. Okay? And just something else to think about, okay? Let's say we're dealing with a very strong acid, like HCl, for example. That's one of our 6 strong acids. If I asked you, what is hydrochloric acid's conjugate base? Hopefully you would say Cl minus. Well, guys, acids that are very strong, like HCl, have very weak conjugate bases. Okay, that is a base. It's a conjugate base, but it's a base nonetheless. It's a substance that is capable of accepting a hydrogen. And this example here, Cl minus, is incredibly weak. Okay. Whereas let's look at the other extreme. Let's say we're dealing with an acid that is very weak, like hydrofluoric acid. It's one of our weak acids. What is its conjugate base? F minus. And it's the opposite. If the acid is very weak, that means that its conjugate base is very strong. F minus is very capable of accepting hydrogen ions. Okay, so I just wanted you all to be aware of that relationship. Okay, now I've pulled up this PhET simulation here, and I want to show you just a little bit of a further sort of visual explanation of the difference between what the words strong and weak mean. Okay, and what is displayed on the screen here is a strong acid. Okay, look at the pH. The pH is relatively low, okay, and that should be for something that's a very strong acid. What I want you to really focus your attention on, though, guys, is these little red hydronium ions right in here, okay? The amount of hydronium ion is going to be a direct indication of how strong this acid is. And if you look in the picture here, this enlarged particle view, there are lots of H3O pluses. And that's typical for a strong acid. There is much dissociation. This reaction goes very heavily in the forward direction. Lots of H3O plus is going to lead to a very acidic pH. Whereas look at a weak acid. Okay, look at the pH first of all. It's still in the acidic range, but it's not as acidic as the strong acid was. And look at this visually. Look at where how many H3O plus ions there are. Are there some? Yeah, but not nearly as many as there were. And that makes sense. Weak acids do not dissociate nearly as much as strong acids do. Okay, so I just wanted to show that to you visually. So what we're going to do, guys, is I'm going to show you the process that is required to solve for the pH of a weak acid solution. And we're going to always start off by looking at something called listing our major species. What are the big players in the beaker? And on this slide and the next, guys, I have a whole series of steps for how to do these problems. Rather than talk through them, I would rather show you a practice problem. Okay. But here's the thing, ladies and gentlemen, and this is not going to be good news for some of you. Every acid-base problem is different. Every single one is unique. You can't memorize a way. You can't say, oh, this is this type, this is this type, because there are too many types. You have to understand the chemistry. And I understand that that is not an easy thing to do. Okay. But we're going to set up, and I'm going to show you how to do a weak acid problem, and then I'm going to let you try one on your own. As I said, guys, a weak acid problem, you're going to be given a Ka value. We're going to start off our problems by writing the major species. And guess what? Actually, you already kind of know how to do these. The way to do a weak acid problems, do you guys remember ice tables from Equilibrium? That's how you do these problems. Some of you may have liked ice tables, some of you maybe not, but it does keep the work in your calculation very organized. So this is the way the AP exam is going to expect that you will do these problems. All right, so I'm going to do number 1 with you. And ladies and gentlemen, all of the work that I write out, if this were, a free response question, all of the work I write out is what the AP graders would expect to see as well. Okay? So it says, calculate the pH of a 2 molar acetic acid solution, should be in there, with a Ka of 1.8 times 10 to the negative 5th, okay? Get in the habit of sort of assessing the situation, okay? We have acetic acid, which I'm gonna write out. And we also have water, okay? We're always gonna have water in these acid-base problems, okay? So guess what? These are my major species. And let's kind of assess the situation. Acetic acid, is it one of my 6 strong? No, it's not. It's definitely a weak acid. And you know what's another hint? We're given a Ka value. Remember, strong acids don't have Ka values. So these are my 2 major species. Those are the only 2 things I have to deal with. And I'm going to get over here to a blank screen. And guess what? Those 2 major species are going to end up being my 2 reactants. Okay, and we're going to predict products here. Don't overcomplicate it. Remember the definition of an acid. What do acids do? They donate away their hydrogen ion, and if that happens, we're going to be left with the acetate ion as our conjugate base and hydronium as our conjugate acid. So there is my reaction. And as I said, from here, we're going to set up an ice table. This should start to feel very familiar. Okay, let me come back to the problem. What was that initial concentration? It was 2 molar. So I'm going to fill that in right here. Okay. I don't care about water. Water is a liquid. It's not going to end up being in my equilibrium situation, so I'm going to ignore it. Okay. These 2 guys, I wasn't given any information about them, so there must not be any there present. Minus x, this should sort of start to feel familiar, plus x plus x. Okay, I'm going to bring everything down. X, x, okay. And if you'll remember from last unit, what we did at this point was we wrote an equilibrium expression based on the reaction above. So there's the acetate ion, products over reactants, times hydronium over the molarity of the acid itself. Okay, and then I'm going to substitute in these values here, or these expressions. And we have a value for Ka. It was given in the problem. Okay, and if you remember back from last unit, what we did at this point to solve for x was we graphed this expression. We went into our calculators and we put y1 as the value for Ka, and then in y2, I put in this whole thing. We graphed it, we found the intersection. If you need to review that process, please go back and watch the video on it. But when you do that, if you've done it correctly, x should come out to be approximately this number. Okay, might be off by a digit or two depending on how your calculator rounds. Okay, now let's come back to what are we trying to solve for? We're trying to solve for the pH. And let's remember, what is it that you need to solve for pH? You need the hydrogen ion concentration. You need H+. Well, remember guys, H+ and H3O+ represent the same thing. And I want you to focus your attention right here. I have just found the value of X. And guess what? According to my ICE table here, X is the molarity of H3O+, which is the same thing as H+. So I can now solve for the pH quite easily by using this equation, which is on your equation sheet. Negative log of, and I'm going to put in that value for X. Okay, and I know this is a free response question and you could use your calculator, but guys, let's practice those estimating skills. Remember, when you take the negative log of something in scientific notation, your answer is going to be relatively close to that exponent. If this value for H+ was exactly 1.0 times 10 to the negative third, taking the negative log would give me a pH of exactly 3. But since this first term is higher than 1.0, my answer for the pH is going to be 2 point something. And if you do the math, it ends up being somewhere in the neighborhood of 2.22. Okay, if you're off by a decimal or two, no big deal. And as I said in the last lesson, guys, I want you to get in the habit of asking yourself, does this answer make sense? And yes, it does. What did we have? We had a weak acid. Okay, it's an acid. Is my pH in the acidic range? Yes, it is. So this answer makes sense. So, ladies and gentlemen, what you are seeing in front of you is all of the work required to get full credit on a question like this in free response. You have to show all of this. I know it's a lot, but it's important. So what I want you to do is to pause the video and try number 2 on your own. It is the exact same setup, just with a different acid, different numbers. So try it. All right, let's see how you did. Okay, as I said, it's the same setup. We have a weak acid and that's it. Okay, so this weak acid, HF, and water are my major species. So if I come over, you can see my reaction up at the top. I've substituted in that initial molarity, filled out my ICE table, set up my equilibrium expression right there. I put it in my calculator, I graphed it, found the intersection point. which happens to be, which is X, and X just so happens to be equal to H plus. Now, will it always? No, but you don't have to memorize that, guys. Look right here. If you've filled out your ICE table, you can figure out what X is. And in these cases, X is equal to H plus. I plug it into my pH equation, and I get 2.46 as my final answer. And that is a pH that makes sense for an acid, which HF is. Okay? So there's nothing actually all that new in these problems than what we did in the last equilibrium unit, but it's just putting it in a different context. Now, what if, I want you to look at a problem here, which we're actually not going to work through. I just want to talk about it for a minute. What if you were given a situation with not just one acid, but two acids? Okay, now in this particular problem, if you'll notice, look at the two acids I'm given. Neither one of those is in my list of strong acids. Both of these are weak. So does that mean we have to do an ICE table setup for both of them? Good news? No, you don't. Okay, look at the statements above. It says the stronger, bigger Ka will predominate. What that means is, guys, the acid that has the larger Ka is slightly stronger than the other one. Now, these are both weak acids, but look at the numbers. HF is a little bit stronger than the other one. Okay. Now, what does that mean? That means if we say that, yes, although they're both weak, HF is a little bit stronger, I can tell that because it has a bigger Ka value, that means HF is going to be contributing more H plus ions to the solution than the other acid is. And here's the great news. When you're calculating the pH, all you need to do is focus on the dominant acid. And guess what? You can essentially ignore the other one. Okay, now please understand, it does not mean that that acid is not contributing anything. It is dissociating some, and it is providing H plus ions to the solution, but it's not providing nearly as many as HF is, so we're going to just focus our attention on HF. And guys, at this point, if I've crossed out the other acid, this is essentially just like the problem we just completed. Okay, it's just one ICE table and that's it. Now, if you had a mixture of acids where it wasn't two weak acids, but a strong acid and a weak acid, guess what? You'd focus your attention on the strong acid only and ignore the weak one. And we talked about how to handle strong acids in the last lesson. If you have a mixture of two strong acids, then you do have to deal with both of them, find out how many total moles of H plus you have, and divide by the total volume to find that pH. Okay, but I just wanted you to, if you ever see a problem like the one displayed in front of you, you do not have to do two ICE tables. Okay, here's something else you might be asked to solve for in a weak acid situation. You might be asked, instead of calculate the pH, you might be asked to solve for the percent dissociation, which, guys, means exactly what it sounds like. What percentage of the acid broke apart, ionized, dissociated? What do you think? Think about what that percentage would be for a strong acid. And I hope you were thinking in your head 100%, because that's correct. Strong acids dissociate completely. Weak acids, not nearly as much. And so this is the formula to calculate it. This looks more complex than it really is. Percent dissociation is equal to the amount dissociated over the initial concentration times 100. Well, guys, guess what? This concept right here, this term, amount dissociated, if you did an ice table for your weak acid, this what's in the numerator, that's X. When you solve for the intersection in your calculator for X, that's what goes in the numerator. That is how much of the acid broke apart. And the one in the bottom is exactly that. It's the initial molarity of that acid. What's on the initial line of your ice table. Okay, now there's two statements here that I'm going to hold off on. I'm going to come back and address them a little bit in just a little bit. I want to have some numbers in front of us before I talk about this concept. Okay, so we're going to look at this question. Okay, we're going to look at this one together, and then there's a second one below that I want you to do on your own. Okay, but let's look at this one together. It says, calculate the percent dissociation of a 1 molar and a 0.1 molar acetic acid, and then we're given the Ka. This is actually two problems in one, okay? What I want you to do just for now is focus your attention with that as the initial molarity and ignore this one just for the moment. Just pretend it's not even there. Okay, so what I want you guys to do is pause the video, set this weak acid problem up, set up your reaction, set up your ice table, solve for X, and then stop there. Okay, if you know how to go further, if you feel comfortable finding the percent dissociation, go for it. But I want you to at least set the problem up on your own. Okay, so let's see how you did. I asked you to write the equation for this acetic acid dissociation, fill in your ice table, set up your equilibrium expression, and solve for the intersection point X. And if you did it right, this is what you come out with. Okay. If you didn't get that for X, chances are, guys, you probably have a mistake in your calculator when you're graphing with that expression right there. Okay. One of the things, remember, that I suggest is put a set of parentheses around your entire numerator and your entire denominator. That sometimes will fix the problem. Okay, now at this point, they asked us to solve for the percent dissociation, which is, what's in the numerator is the amount dissociated. And guess what? That's X over the original molarity, which is right there. So I'm going to plug that into the denominator, times 100, and I get this. Okay, and I want you guys to appreciate that number. Think about what we said. Strong acids, what is the percent dissociation? It's like 100%. And look how much smaller this is. When we say weak acids are weak, we mean it. Okay, this acid barely dissociates. It only dissociates 0.423%. That's not very much. Okay. Now, we're not going to redo this entire question, but what was printed on the slide, it said, what is the percent dissociation for a 1 molar acetic acid solution? And then it said, what is the dissociation percentage for a 0.1 molar? Okay, so I want you to kind of keep this number in mind. And let's think about, I'm going to change color so that they're in red now. What am I going to change? The equation is not going to change. Okay, but my initial molarity is. And this is going to change. Okay, and down here, this is going to change. and my value for X is going to change. And when you graph it out, you should get something in this neighborhood. Okay, now in the percent dissociation, both numerator and denominator are going to change. Because the original molarity isn't 1 molar anymore, it's 0.1. And how does that change our percentage? Okay. Now, there is a statement on the previous slide, and I don't want to cut away from this slide because I want to have these numbers in front of us as I say this. Okay, but I'm going to read you these statements, okay, which I said I wouldn't address until now that we have numbers in front of us. And here's what it says. For a weak acid, okay, yep, that's what we have, percent dissociation increases as an acid becomes more dilute. Let me say that again. Here's what the statement on the previous slide says. For a weak acid, percent dissociation increases as an acid becomes more dilute. And we have just seen that. Okay, the acid originally, that initial molarity was 1 molar, and now it's 0.1 molar. I've made this acid more dilute. And what happened to that percentage? The percent dissociation was 0.423, and now it's higher. And that seems kind of backwards, right? You'd think if the acid was more dilute, it wouldn't dissociate as much, but it just does. And I wanted to prove that to you with some numbers. I didn't want to just say that statement without having numbers in front of us to back it up, because I know that seems a little bit counterintuitive. So what I would like for you to do is to pause the video and try this one on your own. This one is a little bit backwards from what we have done, because this time I'm giving you the percent dissociation, I'm giving you the initial molarity, but I am not giving you the Ka. But ladies and gentlemen, set it up the exact same way. I know you don't know what the acid is, so just call it HA. Set up your reaction, fill in your ice table, see if you can figure this question out. I bet you can. All right, let's check how you did. As I said, this one is a little bit backwards. So we started with an acid HA. Okay, and let's keep your eyes, move your eyes from the top down to the bottom. So I wrote out my reaction, I filled in my ice table, I set up my equilibrium expression, but I did not have a value for Ka. There was no graphing in this question because I don't have a Ka value to graph with. But I was given the percent dissociation, which allowed me to solve for X, which I then plugged into my Ka expression, and I was able to then solve for Ka. So this problem really illustrates why it's so important to write out all of your work, because then it's so much easier to see what's going to go where is your unknown, where can I solve for it, things like that. Okay, so this is just an example of a question you might see. Now, we're going to transition to talking about bases, and you might say, well, are we going to have to learn a whole new process? And no, it's actually a lot of the same understandings. The word weak is used in the same sense for bases as it is for acids. So if you look at an example here, this is ammonia, which is a weak base. Remember what do bases do? They are proton acceptors, and that's what ammonia is doing. Okay, And when we say that this base is weak, it means the same thing as it did before. This reaction will not proceed very far in the forward direction. Ammonia is going to stay, for the most part, as ammonia. Very, very little of it is going to be converted into ammonium and hydroxide, but a little bit will. Okay. We can set up equilibrium expressions just like the weak acids, except instead of Ka, now they're Kb expressions. B for base. Okay. So again, there's very little dissociation. Most weak bases, ladies and gentlemen, do not even contain hydroxide in their formula. Okay, like ammonia doesn't. Okay. They are weak proton acceptors, okay? And this is just another example. And I did this one on purpose because I want you to look at this weak base on the left. And I want you to know, guys, that would I, or the AP exam, would they expect you to look at that formula and just sight unseen know immediately, oh, that's a weak base? No, they wouldn't expect you to know that. But maybe they give you this reaction with water. You would be able to tell that it is a base because if you look at it from left to right, what is it doing? It has accepted a hydrogen ion. So it must be a base. Okay. Also, like if we're doing this problem with it, that compound is called methylamine. Here's another clue that it is a weak base. I'm given a Kb value for it, okay? So that's another clue that this is not only a base, but a weak base. Remember, strong things, strong acids, strong bases also will not ever give, you'll not be given K values. You don't need them for strong things, okay? So we're gonna work this problem together, okay? If you want to try it yourself, you are certainly welcome to do that. I'm going to work this one for you. It's very similar to the process that we have been doing, just slightly different. So the first thing I'm going to do is just rewrite that reaction. That's called methylamine. It's an organic molecule, and it's going to accept a hydrogen. Oops. Where you attach that hydrogen doesn't really matter. I just put it on the end. And you'll notice instead of getting hydronium ions in these reactions, we're getting hydroxide ions. That's why they're bases. Okay, they gave us a molarity, 4 molar. We don't care about water. This is going to be feeling very familiar. And for the most part, this process is exactly the same. There's going to be a little bit of a difference down here at the end. Okay, I'm going to set up my equilibrium expression just like I did for those acids. And I'm going to substitute things in, x squared. And they gave us the Kb value. And now I'm going to graph it, just like the others. So far, nothing really new here. No new processes. And if you graph it, you should get an intersection point somewhere in that neighborhood. Okay, now this is where this is a little bit different than the other problems we were doing. Okay, the last problems we were doing, when we solved for this intersection point, what was X equal to? It was equal to the hydrogen ion concentration. Not this time. But guys, you don't have to memorize this. Look at your ice table. What is that X equal to? It's not to the hydrogen ion concentration, it's the hydroxide ion concentration. We're still looking for the pH as our final answer, but maybe it would be a little bit easier to find the pOH first. Here's the formula for that. Plug in that value for the OH minus. And we should get that. Okay, remember, how do you go from a pOH to a pH? You do 14 minus that number, so here is our final answer. As always, ask yourself, does this make sense? And yes, it does. What was methylamine? It was a weak base, okay? Did our pH end up in the basic range? Yes, it did. So I can feel confident about my answer here. So guys, this process was exactly the same as what we've been doing. The only difference kind of came in here. But don't memorize. If you've set up your ice table, you can always know what X is equal to. Okay? So I want you guys to try these two problems on your own. Number 2 says calculate the percent ionization. Guess what, guys? That is the same thing as percent dissociation. It's just the term we use for bases. Percent dissociation is the term we use for acids. Percent ionization is the term we use for bases. They are set up exactly the same. Okay, so pause your video and give this one a try, or these two questions a try. Okay, let's check your answers and see how you did. So here is number 1. They dealt with a 0.15 molar solution of ammonia. Again, guys, when you find the intersection point, when you graph these things and you find X, X is not equal to H plus anymore. It's equal to OH minus. So you want to solve for pOH first and then find your pH. Again, get in the habit of asking yourself, does this answer make sense? It does. Ammonia is a weak base. Is my answer in the basic range? Yes, it is. Okay, now number 2 was a very similar setup for a different weak base, but at this time, instead of asking for the pH, it asked for the percent ionization. So here's number 2. Notice the setup is exactly the same, except I'm not solving for a pOH and then a pH. I'm solving for percent ionization. Remember, guys, that is the same process as when you solved for percent dissociation. Percent dissociation is a term we use with weak acids. Percent ionization means the same thing, but it's the term that we use for weak bases. And you can see the percentage is still pretty low, okay? That's still something weak. This base is not ionizing. It's not, that reaction at the top is not going in the forward direction very much at all. Percent ionization for a strong base would be 100%. All right, one just final thing that I want to say about acids. Okay, we've seen this vocabulary word before, polyprotic. Acids that can donate more than one hydrogen, like carbonic acid, for example, can donate 2 hydrogens. We would be more specific and call this a diprotic acid. What I want you guys to understand is that with polyprotic acids, these hydrogens are not donated all at once. They are donated one at a time. So you see two separate reactions here. You see two separate Ka values. But here's the good news. If you were doing a pH calculation for carbonic acid, would you have to do a problem that involves two ice tables, one for the first dissociation and another ice table for the second? The answer is no. The first dissociation is always going to be greater than the second. If there is a third, that one will be the smallest. When you are calculating a pH or a percent dissociation for a polyprotic acid, you can mathematically ignore the second, and if there was a third dissociation, because the first dissociation is going to be so much more dominant than the other ones. It's not that this, what's on the screen here, it's not that that second reaction, that second dissociation doesn't take place. It does, but it's going to contribute so many fewer H+ ions to the environment compared to the first one that mathematically it's considered not significant. So what we would do, guys, is we would focus our attention right here and right there only and do an ice table just for that one reaction using that first Ka value, and then we'd calculate at the end of that ice table and then call it a day. Okay, we would not have to even worry about this guy. Okay, we're not going to work this problem, but I just want to show you if you were given a situation like this, okay, you would only need to deal with the first dissociation. So here's what my reaction would look like. The acid plus water. Remember, one hydrogen comes off at a time. They don't all come off at once. And I would set up my ice table under this reaction, okay, and solve from there. I would solve for X, which is my H+ concentration, find the pH from there. I would not have to worry about these guys, okay, because they're mathematically going to be considered insignificant. So I just wanted to show that to you. So let's wrap up this very long lesson by looking at some sample AP exam questions. Like here is a sample multiple choice question, which I'm going to work with you. It says hydroxylamine is a weak base, as shown in the reaction above. Estimate the pH range for a 0.1 molar solution of hydroxylamine, and we're given the Kb value. And guys, remember, this is multiple choice. You don't have a calculator here. But first of all, guys, it's a weak base. I would hope that you could eliminate answer choices A and B because those have pHs in the acidic range. So we know that it's down to C and D, but I want to show you how to solve this. Okay, what I'm going to do is underneath this reaction, I'm going to set up an ice table. So this is 0.1 molar. These guys are 0 and 0. You might say, oh, this is impossible. How could you do this without a calculator? How can you graph it? Well, I'm going to show you. And they give us a Kb value, which is going to be x squared over 0.1 minus x. Here's the good news, ladies and gentlemen. Are you ready? If you are in a multiple choice situation and you find yourself setting up an ice table, let me say this again. If you're in a multiple choice situation, not free response, just multiple choice, you have the permission to get rid of that minus x right there. The thought being that that dissociation, remember x represents how much of this base ionized. That amount of ionization is so small that it's considered negligible. So you can get rid of it. And we were given the KB value. And guys, this is solvable without a calculator. 9 times 10 to the negative 9th times a 10th is 9 times 10 to the negative 10th. If we take the square root of both sides, think about how square roots work. Okay, the square root of 9 is 3. When you take the square root of something with an exponent, you cut it in half. Okay. And then what is this x? Remember, it is my OH minus concentration. You don't have a calculator, but guys, you can estimate this. You can. Okay. POH is negative log of the OH minus. Okay, come back here. If this first term was 1, so if x was 1 times 10 to the negative 5th, taking the negative log, I would get a POH of exactly 5. But it's not 1 times 10 to the negative 5th, it's a little bit higher. So I know that my POH is going to be a little bit below 5. It's going to be 4 point something. So what's my pH going to be? 9 point something. So there's your answer. Okay, I know that's a lot of gnarly math, but that can be done without a calculator, and sometimes you will see questions like this. Okay. All right, I want you to try this one on your own. Again, this is going to involve some math, but try it. It is doable, I promise you. Remember what I said, though, about being in a multiple choice situation. You can get rid of the minus x in your equilibrium situation. Your equilibrium expression, you can only do that when you're in a multiple choice situation. So try this one. Okay, this one, the math was a little bit gnarlier than the previous question, but this is something that could come up on the AP exam. So let me put up what I have. There's a lot to see on the screen here. So I set up my ice table, and I set up my KB expression right there. Please notice I got rid of that minus x because I'm in a multiple choice situation, so I know that is permitted. Then I was given the percent ionization, which allowed me to solve for x. And since I was doing a lot of mental math here, guys, I went ahead and put my value for x into scientific notation and then plugged it in. And that's what I've got right here. Okay, I know the math is a little bit rough, okay? And you'll see again, I didn't leave this as 0.2. I put it into scientific notation because for me it was easier to see how to do this division. Okay, and 18 times 10 to the negative 5th. You might say, well, I don't see an answer that looks even close to that. But remember, 18 times 10 to the negative 5th is the same thing as 1.8 times 10 to the negative 4th. And there is an answer choice that's pretty close to that, right there. Okay, I know that it was not an easy question, and you might be thinking, there's no way I would have gotten that. and I know that the math is tricky, okay, but fill in your ice table, write out your equilibrium expression. It makes it a lot easier to see where your unknown is and what is it you need to solve this problem. Okay, and I would hope, guys, you could at least eliminate answer choice D here, because this is a weak acid. That is a very large value for a Ka. So that's not going to be the case for a weak acid. So at least you could have narrowed it down to A, B, and C. Okay, and last but not least, I want you to try this free response question. This kind of brings everything together. It asks you some questions about lactic acid. So I want you to pause the video and work through these questions. All right, let's see how you did with these questions. The first one you're asked to do is just to complete that Lewis dot structure. And if you count up all the total electrons you have, fill everything in with single bonds first, draw in all your lone pairs, and then assess the situation, you'll see that you do need to drop in a double bond on that carbon on the right, and that's the complete structure there for lactic acid. Part B, number 1, it says the pKa for lactic acid is 3.86, and you were asked to calculate the Ka. And you might have been a little unclear on that, but if you will remember, we talked about what that little letter P means, like a pH. Means that letter P represents the negative log of, and in this case it would be the hydrogen ion concentration. So what is a pKa? A pKa is the negative log of the Ka value. Okay, so if you were asked to solve for the Ka, you just have to undo that log. It would be like solve for the hydrogen ion concentration being given a pH. So, and by the way, this equation right here is printed on your equation sheet should you ever forget it. It's there. I plugged in the pKa, and thus I was able to invert that logarithm and solve for the Ka. And that's a number that does make sense. It's small. Weak acids should have small Ka values. Okay, part 2 asks you to find the pH of it, and I've put my work on a separate slide here. And if you wrote out the formula for lactic acid from the Lewis structure, great. I just wrote HA, which is always okay, guys. I filled in my ice table, my equilibrium expression, I graphed it, I found X, which I knew was equal to H plus, and I was able to solve for the pH. Does my final answer make sense? Yes, it does. This is a weak acid. The pH is in the acidic range. Okay. Last part. Would a 0.2 molar solution of a different acid, propanoic, which is also weak, you can see it's got a Ka value, be predicted to have lower, equal, or a higher pH than the lactic acid solution? Justify your answer. Now, guys, you could, if you wanted to, go through, set up the ice table, and solve for the pH of this one, but you did not have to. You could explain it in words. So the answer is the propanoic acid solution is going to have a higher pH because the Ka for the lactic acid is greater than the Ka for the propanoic acid. We talked about that a little bit. What does that mean? That means the lactic acid, they're both weak acids, but the lactic acid is a little bit stronger. So what else does it say? A smaller Ka value indicates a weaker acid. Propanoic acid is the weaker acid. A weaker acid will produce fewer hydronium, or you could have written H+, same thing, fewer hydronium ions, and thus will give us a higher or less acidic pH. Remember, the lower the number is for pH, the more acidic it is. So this one's not going to be as acidic, so the pH is going to be higher for the propanoic acid. Okay, that was a lot of information. That is actually, I think, my longest lesson so far this year. And I know it's a lot, and you probably feel like your brain is sizzling, and it should. Okay, but that is everything encompassing weak acids and weak bases and the calculations associated with them. So I hope you have learned a lot of something today, and I look forward to seeing you next time.